Hey everyone, I'm going to cover proportional gain in this video. I'll try to keep the video short. I'll cover proportional gain separately from integral gain, and then derivative gain we'll probably cover when I get back. So looking at proportional control, where we'll be concerned with our KP or our gain setting, if we were to initiate a corrective action, it would be in proportion to the change in error. So if we were to look at our error formula, we would take our process variable and we would minus our set point. So we looked at that last class. So depending if a large or small control action is required to correct for a given error, the response will be referred to as the initial controller gain KP. Other terms for KP, sometimes you'll see KC, and then sometimes you'll see PG or P with a lowercase g for proportional gain. Earlier, our last class, we did an example with error. If we looked at an error that had 10%, so that would occur if we had our input change by 10% from its set point, and our controller would respond with a 20% output change. So in that case, our proportional response or gain would be 2. When we're looking at gain, we're looking at the change in our output relative to the change in our input. So here we have our gain equation, KP. Output divided by our input would result in our value of gain. So the position of our final control element or our valve is determined by the relationship between the process variable and the set point. So jumping ahead, since I know you guys have already done this in the lab as well as last term, we know that our valve position is going to equal to its original position, its initial position, plus the gain times the error. That would be if we had a direct controller. Reverse controllers, on the other hand, would subtract our gain times our error from the initial position of the valve. Proportional band is a term that's given to the reciprocal of gain, and we do express it as a percentage. So when we're looking at the proportional band, rather than the output over the input, which we use for gain, we will look at the input over the output. So if we had a gain of 2, we would invert that and times by 100 to give us a 50% proportional band. What that means is that if we changed our input by 50%, our output would change to 100%. In terms of controller actions, typical outputs for digital controllers would be 4 to 20 milliamps. In terms of pneumatic controllers, 3 to 15 psi is a typical output. So if we were looking at an example of proportional gain, so again, the definition of proportional gain is how much you change the input by that would result in an output change of 100%. So in this question, if we have a tank filling example, so I'm going to draw a little tank, and that we had a set point of 50%. If we had a proportional band of 20%, meaning that set point has a range of 20% total above and below, meaning 10% above, 10% below, so that means our input is going to change in the range of 40 to 60%. By doing so, that proportional band change over 20% will result in a valve that is going to change from fully open to fully closed. So it's going to basically go 0 to 100% over that 20% change in our input. So if we look at our 20% proportional band, that means the valve will be fully closed at 40% while the tank is filling, and then it's going to be open at 60% of the level, so we want to stop the filling for the tank if we keep that set point at 50%. Just going to erase my little diagram here because I want to move it over a little bit. So if we have our tank, again I want to draw this a little bit differently. If we have at that 40% level that we want the tank to fill, And then at the 60% level, we want to stop filling the tank at the 60%. So if we want the valve closed at 40%, that means that the valve must occur on the outlet. So if we close that valve at 40%, that means that the tank will start to fill up. If we were to look at 60%, if we want the valve to be open, that means that the tank will stop filling because the liquid will start to come out through the open valve. So in terms of looking at that proportional band, just a second there. So if we wanted to look at a 20% proportional band, we need to find out what the gain value would be. So Kp is going to be the inverse of our proportional band, which is 1 over 0.20, resulting in a gain of 5. If we want to verify that over that 20% that the valve changes from fully open to fully closed, we can verify that by going through our numerical calculations. So you're already familiar with the formula V equals M plus or minus Kp times E. The question doesn't really tell us if we have a direct acting or a reverse acting controller. We kind of need to look at the situation. So if our process variable was falling, so if I take that the tank was emptying, again I'm just going to use my eraser to get rid of my, a little bit of my, oh I didn't want to get rid of that much. Change my color. So if my process variable was falling, PV, my valve, because we are closing when we get down to the 40%, we know that the V is falling. So if our process variable is falling and our valve is also closing, they are following the same action. So we know that it would be direct in this case. Likewise, if our process variable starts to increase and our valve is opening up, so actually our V is increasing at this point, again that follows the convention that we have a direct acting controller. So in terms of our formula now, if our valve started at, let's go in the middle point, if we started at 50%, and then we are going to add, because we have a direct acting controller, if we were looking at the situation at 40%, so let's consider at 40%. Our error in this case will be our process variable minus our set point. So we would have 40% subtract a set point of 50%, resulting in minus 10%. So because our gain is 5, we will say that our error is minus 10%. That means we have 50 minus 50%, meaning we have 0%. So our valve would be closed at 40%. If we go up to our upper range, so the upper part of our proportional band, when we have a process variable equal to 60%, we will verify that that proportional band will give us 100% of our output. So V, going back to our equation, we have M plus Kp times E. Calculating our error at 60%, we have 60% minus 50%, meaning we have a 10% error, but it's a positive 10% error. We'll take our 50 plus our gain of 5 times 10% error. We have 50% plus another 50%, resulting in 100%. So this concludes that a proportional band is 20%. As we change our input by 20%, our output goes from 0 to 100%. So looking at this next illustration is going to show what happens to our output as we move the pendulum position to the error. So on the left-hand side, we have our percentage error. So we can consider our proportional band as well in this case. So let me just bring up our first example. So if I had a percentage error that went from negative 50% to 100, or sorry, to 50%, we have a change in our input of 100. So we can see here in our change in input, we have a 50 minus a minus 50. The magnitude of change on the input is 100% change. Looking at the output, we also go from 0 to 100%. The output changes by 100%. So if we were going to compare the gain in this case, we have 100 minus 0% all over 50 minus a minus 50, resulting in a gain of 1. So that means that we have, if we wanted to invert that, we would have a proportional band of 1 over our Kp, which is basically 1 times 100%. We have a proportional band of 100%, meaning that our input has to change by 100% to achieve 100% of our output. So it may be a little confusing. Just going to erase what I've done there if I can. Maybe a little confusing looking at this in terms of percentage error, but you can if you want it. So for example, if our set point, let's give a concrete value of 50% as our set point. If we looked at our process variable that gives an error of 50%, we know that the PV is actually 100% to provide an error here of 50. Because our set point's at 50, would result in a 50% error. And then if our PV down below was 0, we know that that negative 50 results from PV minus set point, which is 0 minus 50, which gives us a minus 50%. That is where these values come from if you were curious. So again, I will erase this and look at another example. If we were to change the proportional band, so rather than having a proportional band of 100%, if I were to change that proportional band to be 50%, meaning that my input changes over a 50% scale, I'm still achieving 100% on my output. So in this case, we have our output is in a range of 0 to 100. We have a 50% differential on the input. That would result in a gain of 2. So our proportional band in this case would be 1 over our gain of 2. 1 over 2, and we will multiply that by 100%. I kind of went off my screen. So we would end up with a proportional band of 50% in this case, which makes sense. We change by 50%, just proving that we have that matching up with our diagram. So you will notice that depending on the position, if we go further this way with our pendulum, we will have a bigger proportional band. However, we will have a smaller gain because they are inverse of each other. So if we follow going from the blue, we went with a smaller change in our input, so a smaller proportional band results in a larger gain. Using another example to show a similar situation, we're going to be looking at our proportional band and then determining what the gain would be with respect to the proportional band values. So in this example, you can see up here that we have a valve. I'm just kind of highlighting it here. We have a valve, and then we have two positions. So in this case, you can see our valve is on the inlet, where in the last example, our valve was on the outlet. So we want to have a level filling application in this case that the valve will open 100% when the level reaches 35%. So we want to fill the tank on the inlet. And then the valve is going to close to 0% when we get up to 65%. So you can see that our proportional band here is going to be the difference between 65 and 35. So there's two ways that you can answer this. So if you want to look at just the ratio to figure out your gain, you could look at your output differential, which is 0 to 100% of your valve, over the change in your input, which is going to be the difference between 65 and 35, resulting in a gain of 3.33. Or you can just look at it right from the diagram here. You know your proportional band is going to be 30%. And the valve changes by 100%. So you can just do the inverse of that proportional band in a decimal value, and we'll give you the exact same result. If we change the span, so instead of 35 to 65, now we're going to have a bigger change on our input. So we have 90 to 10. We have an 80% proportional band, giving us a full change in our valve from 0 to 100. If you wanted to do the valve, same thing, find out what the the gain would be. You can do the output range, which is 0 to 100, looking at the change in the input, which is our 80%. That will result in a gain of 1.25, or you can just do the inversion of 1 over 0.8 to give us the exact same number. So you can see that when we have a small proportional band, we have a large gain. In the second example, we have a large proportional band and a small gain. So looking at this mathematically, which we've already covered in the lab, we're just going to derive our formulas. We know that our new output of our valve is going to be our initial change plus or minus our gain times our error. So just as we went through the last slide. So Kp is our proportional gain times our error. M is our initial value when we have no error, so the value that makes our process variable equal our set point. V is going to be our new value of our valve output, and then our plus and minus is used for direct acting versus reverse acting. So just simple examples here. If we had a controller gain of 2, and then we had an initial output of 50%, so that's where our set point, our initial controller output will be our M of 50%. What would the new output be if we increased, if the input decreased by 10%? So it didn't give exact values, but we know that our set point is here, and our process variable went down below, so it dropped down here. That means that our error, we know, is going to be a negative value. So that's going to be a negative 10% that you have to take into account in your equation. So if this was direct acting, we would take our 50% valve initial input, twice the gain, times our negative error, resulting in a closure of our valve of 30%. So our PV comes down, our valve comes down or closes. If we were looking at reverse acting, now we're going to use the negative, and with the negative error, we will end up opening up the valve further. So our PV is decreasing, our valve input is increasing. Makes sense for a proportional, for a reverse acting controller. In terms of looking at this in terms of a graph, we have a change in this example of our flow. So we had a water flow level that was high, and then all of a sudden, due to some disturbance, our water level has now decreased. Even though we have a constant set point, if you looked at the water traveling into a tank, if all of a sudden the flow of water decreased, it would heat up a lot more. The water in the tank would heat up a lot more if the water remained traveling slowly through that tank. So our set point would stay the same, and our process variable will rise above our current set point. When we look at A, B, and C, so when we have a proportional band that is too wide, that means that we have a small gain. So A is going to be an example of small gain. So you can see with a small gain that we overshoot and we have an offset. We have an offset from the set point. If your proportional band is too narrow, which is the case for B, that means that we have a large gain. What happens with large gain, quite often, is that you result in cycling. You're forcing your output to change too fast based on the current error. So you're going to go too high, too low, and you continue in that pattern. Your correct value will give you a quarter amplitude delay, which is where we overshoot. And then on the, my pen is a little bit too thick, so let me just redraw that. So you're going to see that the amplitude is going to be, on the negative half cycle, it will be half of what it was before. So whatever your magnitude is here, it will be half, then another half, and continuing on until we meet back with our process variable, or back to our set point. So the problem being, if you use proportional only, you may end up having some offset that you cannot get rid of. So in that case, you will need to find another method of control, which is where the integral or derivative control will come into play. So reading the point down on the bottom, so proportional only control has a characteristic that too much gain will result in the same as an on-off where the process will cycle. So that's where we have for the example of cycling would be B. Too little gain would result in moving the process variable too far away from the desired set point. So in A, we have a small gain, we've overshot it by way too much, and we can't get back. So ideally, we would want to stay with C, where we're in between, and we have picked the appropriate gain. Looking at the final slide, actually no, it's not the final slide, I apologize. A few more slides on proportional gain. If we were to look at this diagram here, this is showing proportional only response. It's assuming that the output is disconnected from the valve. So that means that the output, we're sending out a response to the valve, but the valve is not actually taking in that value and changing the value of that output. So that means the transmitters will not change. So in this example, we have, first we have no error, and then we have a step change where we have a value of 1. If we look at how the controller would respond, what it would tell that valve to do, will depend on our gain value. So looking at, we have a direct acting response for this one. Our error is positive, so because I know my output has gone up, this is an example of a direct acting response. So if we look here at how the valve would respond, we have M plus Kp, or Kc in this example, times the error. We can see the initial valve position, M, is 0. So we will have 0 plus our Kp, if it's set to 1 in the middle example, and then we times that by our error of 1, we will result in a valve position of 1. So that is where we get an output of 1. If you wanted to find out what the proportional band was, you just take the inversion of 1, multiply it by 100. For the top example, if we wanted to know the position of the valve, we would again start with 0 on our M, Kp times E. We have 0 plus our Kp or Kc in this case is 2, and our error is 1. So that is why our controller is now up to 2. If we look at the bottom example, again without stating out the full formula, we have 0 for the valve position initially, plus a gain of 0.5 times our error of 1. That brings our valve position down to a half. So that's where these values come from in this example. If we were to look at the next example, we have a closed loop dynamic proportional response. The controller output is connected to the valve, And then we have sudden change in a set point. So we can have a disturbance. A disturbance can still be considered a set point change. So in this example, if we look at our error, we have our process variable minus our set point. Our process variable is going to be below our set point because we've now increased it. So our error in all of this example will result in a negative value. So as you can see here, we're trying to, when we change the set point, our process variable is trying to respond. The valve is closing, and we are trying to get back up. You'll notice the offset error is one of the main problems with proportional only control. So some degree of error is remaining. I may ask you, what is a problem with proportional control? The error may still remain. If you increase your gain, that may make the system unstable, and a high gain may result in uncontrollable oscillations. So if you can accept some offset from your value, proportional control alone may be good. Otherwise, you're going to have to look at additional methods of control to get rid of that offset. Looking at the final problem, I promise, for proportional control, we are going to look at a situation where we have a valve that is going to need to open and close based on the error. So it's only going to change, or V only changes based on error and the value of gain. So the value of gain set in the controller may or may not be sufficient enough to handle some disturbances, and that's what this example is going to demonstrate. The M value is the initial position of the valve when there is no error. So if we look at this example, what is happening? We have a hot water feed with a constant flow rate. So basically we have a tank, we have hot water flowing in, we have a valve here with an initial position M that is able to balance the set point and the process variable to make them equal to each other. So as long as my flow rate stays constant, we may be okay. However, in this example, it shows that we have an increase in the amount of flow going into this tank. So if we increase the flow rate, and then it could be leaving the tank, so if for some reason the valve position did not change, we could be maximized, or something else could be causing that the valve position could not change, but the flow rate increased. It would not be possible to maintain the same tank temperature without opening the valve further. So my example of it being maximized would not really apply in this case. So if we were in position 1, so say the valve was at 50%, so we will be able to, at a low flow rate, achieve temperature T2. If for some reason we end up increasing our flow rate a lot, you will see that if we kept our valve in that position, the temperature would decrease. The water would be just going through so fast that it would not be able to heat up. So in that case, if we left everything as is, we would not achieve the temperature in that tank that we would want to. So the only option we have then would be to manually manipulate the position of the valve, the initial position of the valve, to meet the higher demand of the flow rate. So if we are to move to position 2, we open the valve to position 2, we are able to then allow more hot water to come through and increase the temperature in that tank. So we're able to meet T2. If you went back then at that point to a low inlet, you will find that the adjustment again may have to occur to the manual reset. The M term may need to change as well for the reduction in the flow. So that is it for the example of how a disturbance may end up making you change your manual reset value.